Well, hello everyone. I think we'll go ahead and get started. I know a few folks will be joining us shortly. As always, I like to open us up in prayer, so let me do that. But let me just mention one thing I'm going to be praying for, and I don't have permission to mention the names of these individuals, but we're also dealing with some of our fellow students who have some challenges, both with their family or personal health. One person is actually in the hospital, and another person, their father was gravely ill and had to go back home overseas to take care of that. And so just keep in mind that we're all trying to be learning some valuable information, but also want to be mindful of prayer and lifting each other up and being supportive. So I'll just include that as well as we just open up in prayer. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course, Lord. I pray that you would help them prepare for a bright future, Lord. I pray that you would give them the skills and be able to assimilate the material in such a way that as they're starting to reach out, getting their first or maybe their um, the next job that they would like, that's going in the direction that they'd like their career to go, that you would help them and guide them in that path. Pray that you would be working with some of the students that are having some physical challenges that have been nice enough to reach out to me, and I'm grateful to be part of that support network. And I pray all of us can be mindful of lifting each other up. Pray also that you would help each of these students to continue in their spiritual formation, Lord, to understand scripture better as they're getting a chance to be studying that, as well as the theological concepts we want to be guiding our lives, and give them interesting and creative ways for faith integration. In Jesus' precious name, we pray. We're going to be hitting it more towards the middle to the latter part of the class, but I do always have an assignment that's a faith integration assignment, and you've heard me speak about this before, maybe in this course, and maybe some of you have had a class with me in the past. And just think about how you're going to be thinking about your future. And so the material that we're covering, how are you going to be integrating your faith? And the easiest and the manner in which we always want to be doing that is in terms of having integrity, doing what we're doing with ethics. But there's plenty of other things that we'll get a chance to talk about more. So what I wanted to do is just do a quick synopsis of things that we've covered so far. I've affectionately have these summary charts that I call the greatest hits. And so I'm just going to go through a few of those. Since this is Thursday, I have it be a little bit more of our lab time. So I will continue to be talking about some of the projects, but I also want to give some time to you all to get a chance to talk about what you have been doing with your digital logic designs. That serves a couple purposes. In the future, you're going to have to be communicating in front of your peers, your progress, and working in that way. So this is one of the behaviors that we're getting a chance to think about. But it's also a chance for me to get some feedback. What is working? Is the material that we're covering starting to sink in? And so that's also useful for me as a diagnostic. A couple of you have already taken advantage of the student survey, so please do that. So I want to continue to get an idea of how things are working. I completely reworked this particular course, and so I think it's working better, but I'm still starting to get the feedback that I need to make sure that it's on target for what you guys need. So that's just another little tidbit that I'll point out. So let me just go over a few things. I'll do a little bit of show and tell of some things that I brought. So far, we've talked about the basic concept of computers. We talked about this performance concepts, and I always think of Gigaflop as an example, but they have some more specific examples that they talk about in the textbook. And they do have a rigorous academic backing, what Stalling has done with this textbook. And so the things that they developed are more rigorous than that, because you can think of, if you have some kind of a standard that doesn't keep in mind exactly what you're doing, like what type of instructions are you trying to execute, that's going to make a difference. Now we're just getting into this next section of computer systems. And so I'm just going to go short of this, will be in this arithmetic and logic. Now, there is like one or two of these first chapters are kind of long. The first chapter, and I believe this chapter 3 are long, but I think you'll find that after that, they get a little bit more manageable. And that was one of the comments that I did get from folks as they were looking through the material. So we have the von Neumann architecture, and Stalin throws in a fourth one, is you have the IO, memory, and CPU, and then you have the system bus. Sometimes I just like to group that in with the IO. And one of the things about this picture, we can sort of see this von Neumann-like architecture actually flowing down into the CPU itself. It has memory, it has a CPU, if you will, in the arithmetic logic unit. It also has the IO and the interconnections, and so that's kind of like that. And you could sort of say the analogy starts to break down a little bit, but within that control unit, we still see some things that are similar when we look at that level. I showed you a picture of a motherboard for my Dell desktop. This is just one that they have in the textbook, a little bit more of a focus processor that this could plug into a motherboard. And so you could have multiple separate computers. And so maybe you're developing a cluster, and this would be one of many that you would have that you're using. So that's something that you have. There's transient computing, that we're getting to a point where we can't put any more power in. The frequency is kind of getting to a point where we're not be able to go much faster. And that's where we started to see the increase in using cores, still trying to push the number of transistors that are in complicated circuits. That continues to go. We get into more details of the von Neumann architecture, where we're going to be getting into details. And so some of these are just a reminder of these names: a program counter, the instruction register, lots of different types of registers. And then the way that we think about the memory, where you're going to have your data and your instructions are going to be in slightly different locations. And so that's something that you'll be observing as we start to be thinking about the assembly language. And we'll get exposed to an ARM architecture in that regard. This is a high-level view of the basic instructions that what goes on in a computer, and it's a fetch, execute. It has to fetch everything it needs, get things from memory, stick things into the registers, tell the arithmetic logic unit what it's supposed to be doing. And so then it says when you're done, then you go back and say, I'm ready to do the next instruction. You can see this is why you need a program counter to tell you where you are. And then when you're finally done, you complete that and you halt. We've had a couple ways that we've looked at memory. This is getting a chance to be thinking about that a little bit more globally, going from the CPU that has registers. We talked about this interesting thing that cache makes a difference in performance. And it even shows up in some other places like a hard drive. And I'll show you that in a minute, just what a hard drive looks like, for example. The main memory, we started to begin to think about these different terms of what these means. We have dynamic RAM, SRAM, and then these other things that I've mentioned. We get into the solid state memory, where a lot of the hard drives are being replaced by these flash memory of things being aggregated together. And then we can have offline storage, so maybe a physical hard drive, or you start to have some things that are put off in the cloud, and a more legacy type of technology is magnetic tape, that is not kept active, where you can access it, but it's recorded, the information, and then it's put into an archive, and so that's something that's there. There's a difference between the way that instructions versus data, in terms of how the distribution of what we see, what is the memory address, that the instructions is like one line at a time. With data distributions, it's a wider one. It can be chaotic. You're doing one subroutine or another, one program calls another. And so that distribution is slightly different. There's different ways in which we access information. Sequential, this would be more of what you would see in a program. You can have direct access, and so you want to effectively have the CPU thinking that it's getting directly to what it has. Random access, this is where you don't know. This is the amazing thing about computers. It's not made for one thing. It's made to be agile, programmable. And so you need to have a way of looking at that. And finally, associative, you can start to be thinking of collecting things and getting them from storage, if you will, in a group. And associative, one thing, all you can think of, like wherever you live, you can have like everybody on your block is called to attention. We had our fire drill, and so we were all called to attention in our building. And so it wasn't anything that was going on in East Campus. And so that can be a way of thinking about associative. This is a better image that shows you the advantage of caches. You know, first of all, having one, that was great. And then what we found 3 or 4 is where things are at. And it actually shows you some improvements. And so that is the kind of tendency that we see. Talking about memory, it's like you have these different memory modules. And how do you double your memory? Basically, you stick in one extra bit, and then you have 2 identical modules, and then you say, I'm going to either go to that lower module, I'm going to go to that upper module. And so this is how you start to aggregate things together. And I'll stop sharing my slides in a minute, but this will be a little bit harder to see right now. But this is the stick of memory that I showed you, the Micron memory for an older computer that I had that has since reached its end of life. And this is just that pyramid now, just focusing on RAM, some of these technologies that are starting to really be some interesting things with some of my work in neuromorphic computing. These types of technologies can be called memristors. There's different ways, not only going from one state to another, which is a primary function of memory, but if you think of computing memory, which is a concept in neuromorphic computing, it's how it goes from one to another. So it actually has the ability to do some computing as well as the memory. This is where we were getting a chance to be thinking about how things works in a hard drive, and I'll show you a bigger image of this. But this is an older hard drive that I have. Maxstar was a really wonderful hard drive company. It was bought by Seagate, and so it's assimilated into that. But I'll give you a little bit larger view of that in just a second. We talked about RAID. And so you can think of that all of your computers, or as a minimum, are running on RAID level 0. This means that there is no redundancy. So this gives you the maximum return for your hard drives, but there isn't anything in terms of trying to reduce risk if you lose one of those hard drives. The most rigorous and the most that it takes would be a complete mirrored one. I talked about that more than these other ones. And then you have these other types of things. We talked about error correcting codes. And here are just some other ways of how, not on a whole hard drive, but some of the information, depending on how complicated these codes are, we can actually, if we do have a portion of that hard drive that goes bad, we still have another area that can help us to get a chance to recover that. We talked about single bit error correcting codes, and you can go to a lot higher levels. And finally, this is where we're at right now. We're starting to go away from thinking about memory and start to be thinking about I/O modules. This is a high level view. And so basically all of your externals, there has to be some kind of a translation to then have that be put into the system bus, which then can be routed to the CPU, stored into memory in a different format that is what is needed inside the computer. These are all the possible things that can take place. This is a little bit more detailed view of that. And so, but it's really a translator is the heart of what's going on with that. And I'll end with this because we haven't talked about chapter 9 yet, but this is where we start to see a computer with hardware and software. There is a merging of those two. And with your digital logic design, and you'll get a chance to see this a little bit with your Arduino kit, you can actually program in hardware just as the same way that you can program in software. And sometimes it makes more sense to do one or the other. And we're going to start to be talking about this instruction set to see what that means to be programming things in that way. Okay, I'll just briefly do a little show and tell here. It's make it so it's going to be larger. So I showed you this last time, but just to make a point, what we see that there's multiple chips on here, and the way that they aggregate that, and so there's 2, 4, 6, 8, 16 chips, 8 on this side, 8 on that side. And so those are exactly the same chips that are brought together. So you can like have a 16-bit word by just having all those chips used together. And I'll just show you this a little bit easier now because it's a bigger image for you. So this is at this time when I bought this, there was a time when having 250 gigabytes was like a really large hard drive. And so that's what was here. You can see some of the control electronics here. I have like a Seagate 18 terabyte that I just put into my home server. And this whole thing is encased, and I don't know what, I think they put helium or something like that, rather than having it exposed to air. So this is not like that. And so things, air and dust can get in here. And so that's one of the things that you want to avoid. Might be a little bit hard to see, but you can see like those gold things on the bottom. One of them is for power, and one of them is the serial input and output data lines. It's called the SATA interface. And then up in the top, you may not barely be able to see it, but you can see like there's a circular thing up here, and that's like where the platters are. And I'd have to go look up just to see how many platters are in there, but that's something that you have. And then finally, the one thing I'll do for show and tell, you guys are using a Arduino Uno. This is an Arduino Nano. So this is an example of something that's smaller. And I was showing you an analog circuit last Thursday. And so that's all you need. And literally you can start to be programming an Arduino unit without actually putting anything on it. And so it's kind of cool that that's something that we're able to do. Okay, Ryan let me know that he's having some technical challenges. Well, we'll just work with everybody. One of the things I found, if depending on how good your internet is, turning off your video is one of the ways that you can solve that to a degree. Of course, for me, I like to be seeing all your wonderful faces just to get some feedback that if what I'm saying is going well, and hopefully not putting you all to sleep, because that's not what I want to do. So anyway, so that's just a little bit of a heads up on a few things there. Well, let me pause because I want to give a chance to see if anybody would like to share about their digital logic project.
I can share, Professor.
Okay, Wasim. I think I've said it so people can share their screen, so feel free to do that.
Professor, can you hear me?
Yeah, I can hear you.
Okay, I'm gonna share. Okay, so my idea, my project is for a smart nightlight that only turns on when two conditions are met. When motion is detected and when the ambient lighting is low. So okay, let me go to the tab. Okay, and it has a high and low brightness setting. So let me run this. So let's say the high brightness is on, but there's no motion detected and ambient light is too high. Nothing will turn on. Say motion is detected, but ambient light is still too high, nothing will turn on. If both conditions are met, then the the high light will go on because high brightness is the setting that's the switch is set to. If you switch to low brightness, the low light will turn on. And again, if not both of the conditions are met, then neither light will turn on. So yeah, that's one of my logic examples.
Well, thank you very much, Wasim. And I'm just trying to underline this fact. Literally, what Wasim has demonstrated is he programmed in hardware. And one or two of you have come up and let me walk alongside what you're doing. And that's, you're doing the same thing. Who would ever thought with just a couple of these digital gates, you can actually do a program function. It's like you go to a store and the doors automatically open. You could think of that. It's not exactly what Wasim is doing, but the same kind of thing. Wasim has this way of either having a high or a low. You can there's a lot of interesting logic, and he actually even found another thing in there that I hadn't talked about when I introduced the digital logic tool. And so that's always kind of fun for you to explore and to try things. So thank you very much for sharing that, Wasim. Does anybody have any comments or questions that they have for Wasim, or things that you've observed? Okay, well, let me offer it up if some other folks would like to share. That would be great. And one other thing, while people are thinking who wants to go next, like for Wasim, I mentioned that having like 3 circuits. And so what Wasim, I would say that was actually more complicated than what you would need, say, for a first one. Say for Wasim, it could be the first one be a low light, or maybe you wouldn't even describe it, just that you have a light. And then he has get more sophistication, and he has a low light and a high light. And maybe another third version might be a little bit more complexity of, say, being able to select between a low and a high under some kind of a condition. But all of that looks really good.
I don't mind presenting one of my things. I just need to do one of them right now, all 3, or do you want to do all 3?
It's really up to you. Having 3 is great. What I can share my screen and just quickly show you that. But I would say that's going to be a little bit more complicated. And if you want to try that, I would say that towards the end. But also, I like the way how you're linking what you're doing with what you're going to be doing with your Arduino. You can see how there's relatedness between these three different projects. There are very different domains, but really all of them kind of fit together when we're trying to think of the big picture of considering computer architectures and organization, and whatever we want to do. Say some of the projects you're thinking about, you're going to eventually run them on a phone or something like that, or a standalone thing with a microcontroller, which would be more like what we're doing with an Arduino. Anyway, the sky's the limit. Some of you guys working in cybersecurity, you could have some interesting ways of augmenting security in one form or another. Right now, going to multi-form factors is important, but also having a biometric, including that, whether it's a thumbprint, facial scan. That's one of the things that's now starting to catch on. And so you can see there's some cyber physical kind of connectedness that's going on. Okay, well, let me go ahead and I'll share my screen and go over a few things. Let me just pull up my digital logic, and wasn't going to focus on that too much today because we're wanted to make sure we start to be thinking about what comes next. But for Isabel's sake, I'll mention one thing just by showing this. So, and then I'll just go over some of our other project works just to give you a heads up. And what I would recommend, some of you said that you don't have your laptop or computer in front of you. I'd recommend that you have that, especially on Thursday, because think of Thursday as a lab. And so a lab means it's hands-on stuff. And so I want you to have a chance to be doing that. And so what I have here, this is a counter. And so if you have a counter, it means that you have to have a way that the information comes in and it's triggered. And so that's something that you have to be thinking about. And so I have a clock. And so when things are clocked, this counter is going to go up. And so let me see, I think there's a single step here. Let me see if this works. So I'll kind of load this up. I tried this in single step mode. It may not be the right button. Okay, well, let me just play it. So what happens for this output here, it's like every fourth one, this will go on when it reaches the max methylation. So I have to set everything up so there's something that's sensing. The sensor is set to be able to read that. And so you can see this, the clock is going in, but to activate it, I have to put all these things together. So 1, 2, 3. And so every fourth one, this lights up. And so this is kind of in sort of indicative of what you're trying to be thinking about, Isabel. But what I would do is first is just to be focusing on some of this basic logic, and which I think you've already got it framed out, and just trying and to be thinking about time management of what you think you're going to be able to accomplish. So, but thank you, Isabel, and thank you everybody else. And for those that didn't get a chance to share, maybe you're having some comm challenges, why don't we go ahead and have a chance to be doing that a little bit either next Thursday, or if you want to spend some time one-on-one, we could be doing that as well. So since the next one that we're going to be doing is the Mars project, and so this is where we get a chance to be thinking about an ARM processor. And so instead of just thinking about things from the digital logic perspective, which was the first project, now we want to begin to think about things from how we engage in the language of the CPU. And so we can see how there's some major sections that show up here: the .global, the .text, the .data here, and you can open up multiple files at a time here. Let me open the one that I already shared with you, the hello world. So it's the same kind of thing: the .text, the .global, the .data, and this actually had another one where we have a specific message. And so since we've gone over this a couple of times, so basically we have two syscalls. One is to print out a message and one is to end the program. But to do these syscalls, we have to load everything in before it actually does that function. You might remember this this one chart that we have here. And so we have this load, and then we fetch, and then we execute, fetch and execute. Well, we have that same thing that we're seeing here in this program. We have to fetch all this information. We have to be communicating to the CPU what is the syscall. And remember that the syscall, the first one is 4. So if I go to the syscalls, 4 is a print string, and the 10 is to exit. So those are the things that we have here. And then we had a couple other sample type of projects commands here. So let me just do a quick round the virtual room and get some responses. How many people have tried this Hello World program in their Mars ARM processor emulator? Anybody still having challenges in getting that to work? Okay, I'm not getting too many responses, so I don't know what that means, because I want to help you. And so this is, let me just ask one more time, maybe whatever way, if you want to put in the chat, you want to be putting a thumbs up, you want to go off mute, whatever works for you, just let me know what you want to do. Okay, for those that haven't tried it yet, this is a lab. So go to Canvas, download it as we speak. Let's get some positive reinforcement that you guys have got this. So, um, okay, so under the project resource information, download this example to Hello World. So how many people have downloaded that if you haven't done it already? Why don't you open it up? Isabel, Josiah, you want to give that a go?
Yeah, I'm loading it up right now. I've already had it downloaded. I just haven't like run the program.
Yeah, because I want you to get familiar with some of these things that I'm showing you. Because I think it's going to break down the mystique, and you're going to see it's going to be fairly easy to work. I'll give some people a minute to do that. Andre, you had mentioned that one of your projects is a vending machine with buttons to simulate the coins and bill selectors and dispense motors and change return for the outputs. That's the gist of what you have. So that sounds really good. And as I said, for other folks, like think of a high level abstraction, get something basic working, and you can always add to it, but I want you to go from success to success. So give that a go. So if you have any more questions you want to talk about, please feel free to put that in the chat or reach out to me. Okay. So just as a reminder, what we see here, this is the program. This is the most readable fashion that we have in English. Lots, you can see that there's tons of comments here. We have these main sections that are part of this program. We have these specific commands. So these are these directives, and so we have the dot text here, the dot global. You need to have a main, and so that's going to be something that you want to have. And so here, this is how you have a call. So this is actually pointing to the memory location that has hello world in it. So you want to make sure you take a chance to be doing that. So these are the basic instructions. And then we have the pseudo instructions is like that level below. I showed you an example how I believe it was the LA expanded into 2 different commands. Let me just try and. So we saw that it does this LUI and ORI versus just having this higher level here, this LA. So there's 1, 2, 3, 4, 5, but when it's compiled 1, 2, 3, 4, 5, 6. So that's one of the characteristics that we see that's there. Well, let me try this other one. This is not sure if this will work, but I can give this a go, see if it'll. Okay, so this one's a little bit more complicated. But it's trying to, this is trying to demonstrate some simple MIPS instructions. We have the same structure, the global, the dot text, we have the main, we have the dot data. And so here we have 2 pointers of value and Z. So we have value there and Z. So the first thing is we load immediate this value 25. So that's loaded into register T2. So right here. So let's try and do this the single step mode the way we did on this other one. So we'll go to the execute version of this. So does that, and so we put the value of 25. So we load immediate the value of 25 into T2. 25 is in T2, we see that. This is just a number of the registers. There's a total of 32 registers for a basic ARM processor. And we go to the next one. This is another one of these things that it breaks it up into two things. So we have this behind the scenes one that's here. And so this is actual a physical address that's being loaded here. So this is it needs to know where to get that information. So we have that one. Then we actually do the add. And this is where we're going to be adding what is in T4 and T3 and put it in T4 and 2 are added into 3, if I've got this convention right. So right now we don't have anything. Yeah, I think I have this backwards. So 2 and 3 are added and stick into 4. So right now 4 is empty. So if I click on this, we get the results. So 25 plus 12 is 37. We see that. And we want to store the answer in Z. And so Z is another word that we're going to be leveraging. Oops. So this is broken up into two parts as well. So first of all, we got the directive to so it's moved to a register, and then the register is going to be moved to a memory location. So this is the memory location. And we have another one that we do a subtract. We subtract 2 and 3 and put it into register 5. So T5. So the difference between 25 and 12 is 13. So we see the addition and we see the subtraction. And finally, the last thing we do is doing a clean exit of like we did before, that we have this syscall 10. So this is a second program we're getting a chance to see. And so start with this one, just see if you can start to get some basics here. And literally a first program could be, instead of saying hello world, say I love being at APU or whatever, you could just have some basic type of program to just start to get you familiar with what you're doing with assembly language. And then we can start to do something a little bit more complicated, but this is just trying to give you a survey, an introduction, a glance at what assembly language program is. So that would be what I'd recommend that you do on that front.
Quick question.
Sure.
I copied all the code for the hello world thing, but it doesn't give me the option to run it.
Okay, what you need to do is, if you're in the edit, so let's make sure I go to the right hello world, you need to go to run.
Mm-hmm.
And then click assembly. See this
It's grayed
button here?
out. For me.
Well, let me stop sharing my screen and let me see what you've got. see if I can quickly, if you don't mind sharing your screen.
Yeah.
And because if you are having challenges, others people could just as easily have it. One of the things that may be going on, I would recommend for starters that you just download that ASM file and open it directly, because there may be something subtle that you're missing here.
Okay.
And let's see if we could figure out what's going on. But I like what you're doing.
Which is that in
Project
resource?
resource information.
Okay.
And if you scroll down to the second one, right there, download that file. Now, one thing that's a little bit quirky about, you're gonna have to navigate to where that is. So you can do that the first time, or maybe you just want to move it to a place that is easier to get.
Should be in downloads there. Oh, wait. Uh,
You have a Mac or a PC.
it's a PC.
You can actually do it either. If you just put it at the top level of your home directory. So, or any place else that maybe is not so many folders down. Make
Should
it a
do
little,
desktop.
yeah, just so you can find it easily. So if it's in your downloads, move it to your desktop. And then try opening your desktop. You may have to go to,
There it is. Okay.
now try going to the run and see if that will open. Yeah,
There
there
we
you
go.
go. So this is like step 0. I want to have people have a chance to have a successful experience of starting something. And so this gives you like your gold template, and see if you could start to go back and forth and see what you might be missing. There might be a slight typo, but give that a go. Okay.
Thank you.
All right. Well, thank you for sharing. And like I said, it's probable that some other folks are having some similar challenges, and so was a good thing to make sure that we all share. All right, I'm just gonna finish up with one other thing. And so I'm trying to, part of our lab time, go to the next projects. And so the last thing that I'm going to be sharing is the Arduino. And so remember I showed you what a little Arduino Nano looks like. So this is just a downsize of what we already have. And so I have several of those, but I also have some of these Arduino Unos. And so this is the same kind of program that we were using in assembly language, Hello World. And literally, you could just hook it up like this, put this into your USB, make sure that you're connected to it. And with this, you could just open up the serial port. So the serial monitor, I don't have it hooked up, so I'm going to get an error message. But and then it would actually, you can get a chance to do this very simple program. And there's basically 2 parts. There's a setup, and then we're just constantly printing this thing out. I think this may be just a single time through, so you're going to see it print out Hello World. So every time you run this, you'll get that Hello World. This doesn't have a loop. And so this is one of those very basic programs that comes with the Arduino. Examples, basic. I have to figure out Well, I'm not gonna try and do that real time. I'm pretty sure it's in here, one of these places. But that gives you an idea. Okay, well, let me stop sharing my screen and see if there's any other comments or questions that people have.